Hello, everyone, and thank you for joining us to this webinar. Today, my colleagues Carolina Migliorelli, Paula Subias, and myself, Luis Marte, that we are data science research in the digital health unit of Acute, are going to present this webinar titled Explainable Artificial Intelligence for Predicting Acute and Chronic Stroke Outcomes. Please, if you have questions, ask them in the chat, and we will discuss them at the end. Okay, and remember that the session is going to be recorded, but the names or your names will be delayed. Okay, this webinar is within a series of webinars from TRUSTroke project. TRUSTroke is a European project that is formed by 13 partners around Europe. Gather academia, industry, and healthcare centers. This project was born in 2023 to achieve several aims. The creation of a federated learning network to ensure artificial intelligence robustness and trustworthiness. Create also an application for patient empowerment. Trustworthy and validated artificial intelligence integrated solution for stroke risk assessment. Also, achieve a flexible and scalable platform for continuous upgrading and a proof of concept study of TRUSTroke platform in relevant application environment. My colleagues and I forming part of Eurecat. Eurecat is the most important technological center in Catalonia, Spain. We are more than 700 employees, and we are participating in over than 160 strategic research projects that are involved in many fields like big data, nutrition, security, biotechnology. Concretely, we are in digital health unit that it's involved in different projects related to integrated care, clinical data science, biomechanics, and healthcare innovation. Today, we are talking about digital health, machine learning, digital health, also the uses of machine learning in the project TRUSTroke, explainability about these models, and finally, ethics and artificial intelligence. Okay, first, digital health. Digital technologies are in our life for a long time ago, enhancing communication and information. Digital health is the application of these technologies in healthcare, leading to a more personalized, efficient and precise medicine. Although the term digital health has been around for many years, we are currently living a revolution in this field for two principal reasons. The first one is advances in data-driven methodologies during the beginning of this century, particularly in artificial intelligence. And the second one is the pandemic that already 4 years ago, that the pandemic of COVID-19 in 2020 that increased the efforts and revenues in digital health to keep healthcare service during the pandemic. So let's start talking now about artificial intelligence. What is artificial intelligence? This is a field of study of computational science that addresses tasks related to human way, like reason, learning, or interaction with the environment. Let me simplify this intelligence, and we can see the natural intelligence like the accumulation of experience to generate effective rules and strategies to perform a task. Okay, but how we can translate this technology, this intelligence to computational science? In classical programming, we define explicit rules to perform tasks based on a specific condition. This system relies on predefined logic. For instance, consider an SSC recommendation system for example, stroke patients, where patients input their age and health condition, and then the program responds a set of exercise that previously was taught by a therapist. Then, artificial intelligence is capable of learning how to perform a specific task Instead of explicit programming, this learning process involves generating rules from related data. Then these rules are used to predict values for a new dataset. This concept is commonly known as machine learning. So machine learning is a field, machine learning field is a subset of artificial intelligence. From now, we focus on machine learning area, okay? So machine learning can acquire knowledge through 3 different ways. The two of them are involving learning from data. These are supervised learning and unsupervised learning. In supervised learning, in this approach, we provide the model with labeled data. The algorithm learns to map input data to the correct output, enabling it to make prediction or classification of new data. On the other hand, unsupervised learning feeds the algorithm but with unlabeled data. Unsupervised learning aims to discover inherent relationship and hidden patterns within the data set without predefined target labels. Okay, and the last one is reinforcement learning. This kind of learning is closely mimics natural learning process. In this case, the model learns from its environment through a system of rewards and penalties instead of processing data. The model receives a reward when it approaches the correct answer and is penalized when it makes a mistake. Okay, now we understand kind of the fundamentals of machine learning. Let's explore their capabilities and function. Okay, there are a lot of machine learning capabilities, and machine learning does a wide range of tasks. But I want to enumerate some of them more related to or more relevant in healthcare. For example, classification, que es the determination of an object a specific class. Also, related to classification is clustering. It's similar, but the classification in this case is based on the inherent similarities of data. This can be useful for clustering patients or detect anomalies. Forecasting is the capability of understand or predict patterns in serial time data. And also we can extract continuous values from a feature of data. Also, there are others capabilities of machine learning related to language that are natural language processing, NLP, and large language models, LLM. Natural language processing is the capacity of the machine learning to understand our way of communication. And LLM is the opposite, is the capacity of machine learning to communicate with us in the same way. These are on fashion because they are the capabilities of the ChatGPT, for example. Finally, image recognition is the identification and interpretation of objects or patterns in an image. Okay, next we are moving to the kind of data that machine learning can interpret. For example, related also with healthcare, we have text or voice. It can be useful for medical records or medical history. Also, time series. It's quite important in medicine because you can see data in time. For example, biomarkers like cholesterol, glucose, but also is important or relevant for management. But you can see the number of patients or admissions in time. Also, image like tag or a scanner and tabular data. maybe tabular data is one of the most relevant in healthcare because medical records, electronic records, are structured in this way, with observations in the rows and features for each observation in the columns. Okay, now I want to explain, to enumerate some of the machine learning algorithm. There are a lot, and we can talk about each one a lot of things. So I want to enumerate, and later my colleagues explain some of them. For example, linear regression, decision trees is good for classification and regression, support vector machine, ARIMA for forecasting, logistic regression, that is a regression for classification, or the famous neural network in deep learning. Okay, after the application of a machine learning model, it's mandatory to evaluate it, because we need to judge the performance with a metric of the model. So now I want to talk about evaluation, but I focus on classification metrics, okay? Usually, before training a classification model, the dataset to generate the model is split into datasets, training and test. Of course, training is for training the model, and test is for evaluation. Data test will be used to assess the model. We apply the model into a test, obtain a confusion matrix. That is a tabular visualization of actual true labels and predicted labels. From the confusion matrix, we can extract different metrics, such as accuracy, sensitivity, precision, el area under the ROC curve, or el F1 score. After that, we can optimize the results of our model. First, we can optimize the parameters of the algorithm. But also we can use another typical method like cross-validation that allows to train model with different set of data. Then it's quite important to take account that to choose the proper metric for evaluation and optimization. I put an example. For instance, in the context of TRUSTroke, in a stroke recurrency classification model, for example, to predict if a patient will have a recurrency or not, it's mandatory to find all the possible recurrent patients. So we must focus on sensitivity. That it's the proportion of positive subject correctly identified. But if we do that, this is in the detriment of precision. That is the capability of the model of discriminating classes. Also, you might focus on area under the ROC curve or F1 score, which integrates sensitivity with other metrics. So you have to be aware of these elements. Okay, finally, about the introduction. Machine learning is one of the most important assays in digital health now, because it leads to innovative solution for all challenges. That is improving healthcare at the same time that saving time and saving cost. Actually, machine learning can be useful for develop tools for patient contact, like robots or chatbots, but also for caregivers professionals, that like in tools for decision making, diagnosis, or prevention. That's all for me. So now I pass the floor to Carolina, who will explain you the machine learning models used in TRUSTroke.
Thank you, Luis. I will share my screen. Okay, hello to everyone. Well, what I will explain in this time time slot is a little bit what we are planning for TRUSTroke project. And to put you all in context, here we have the main technological blocks of artificial intelligence in TRUSTroke, okay? So what we are planning to do in the project is first, in each one of the local hospitals, to develop a common data model. This common data model that is developed in Work Package 3 harmonize all the data that we will then train in a local EA models, okay, that is developed in Work Package 4 and is the purpose of this talk and what we will extend later, okay? So all these models in different hospitals, these local models that will be trained in different hospitals will be aggregated in a federated learning platform that is being developed in Work Package 2 in order to create this global artificial intelligence model that will be used for the hospitals that provide data, but also for the hospitals that do not can provide data. Okay. So in this sense, which questions we want to answer with these models? Well, the clinical endpoints or questions that we want to answer is, for example, how can a decision on the procedure of a patient that is admitted to the hospital with a stroke. What is the probability of early support discharge of this patient, or what is the probability of incomplete recovery? This, for example, may be treated as classification tasks. But also, we can ask the model, what is the probability of readmission to the hospital, or what is the probability of a stroke recurrency? And in this case, we can treat these problems as classification or forecasting, okay? So what is the type of data that we will find in this project? Mainly, the data that we will find is tabular data, because we will work with structured data from electronic records or other data useful to identify the patients. Okay, here I put you here an example of tabular data. This is not from the project. This is a public data set that for detecting in the general population if the persons will have a stroke or not, okay? But for the purpose of an example, it serves us to understand how the data may be. We can have categorical variables also mixed with numerical variables, okay? So this is the main type of data that we will be treating on the project. But also, we have this other type of data that is time series data. Even as we are seeing this as a tabular data, all these rows in this case are linked by the month. Okay, here we have only one subject where we are measuring different values, one per each month. Okay, and this would be an example of time series. Okay, where we want, for example, to detect the recurrent stroke, when the person will have a recurrent stroke. No, this is a simulated data based on what we are planning to have in the future of the project. Okay, so in fact, even as we are seeing this as a tabular data set, in fact, this is a time series. Okay, where we have different measurements a long time, and we, for example, want to predict these measurements in this exact point, okay? So just to make you an idea. Okay, so for tabular data, which algorithm is better from a practical point of view? Well, in machine learning, the main way of working is from trial and error, no? It's a general practice. I mean, we test different type of algorithms, and then we choose the ones that perform with our performance measurements that perform better. Okay, and it also depends a little bit on the complexity of the problem, which algorithm we will choose. Okay, so if you are interested in different type of algorithms that are used in stroke treatments or in general in healthcare, here I put you two papers that discuss this and analyze different algorithms and their performance in healthcare tasks. So if you want to delve deep on this is a good starting point. Okay. In general, depending on the complexity, we have simpler problems, and simpler problems can be solved with simpler algorithms. And it's a good practice to use these simpler algorithms when we can. Why? Because these algorithms are easier to understand, are easier to train, and are good for small classification problems. For example, logistic regression is a good algorithm if the problem we want to solve is quite simple. However, in the stroke outcomes measurements and prediction is a complex issue. Why? Because we have a large number of variables, because we are dealing with real data that may have missing values, imbalanced data, outliers, and etc. And also, but because we may find nonlinear relationships between our data. Okay. So in this context, for tabular data, tree-based models are generally the ones that perform better in these conditions, okay? And a question that often is discussed is even better than deep learning, and the answer, at least at this moment of time, is yes, okay? In general, they are performing better than deep learning for tabular data. If you want to know more about this, I recommend you this article that is from Neurip's conference, where this is discussed and also analyzed it from a practical point of view, and the answers why tree models still perform better than deep learning are a little bit discussed there. So I recommend you this article, okay? So let's start with the most basic tree-based model, that is the decision tree, okay? Imagine here we have a very simple example where we want to assess the risk of recurrence at discharge of a patient with a stroke, okay? So a decision tree is this structure where each internal node represents a feature, for example, age, BMI, smoker, and each branch represent a decision rule, okay? So for example, here age, we could make the decision for patients that have less than 50 years versus the patients that have more than 50 years, and so on with the rest of the features. At the end, we will have these classifications, for example, low risk or high risk in this example, okay? And one key concept here in decision trees is how to decide how to split the data. And this is where Gini impurity comes on, okay? I won't go into the details of the maths behind Gini impurity because, of course, we don't have time. But what we do in decision trees is split the data in a way that we minimize this impurity, leading to the most distinct classification groups, okay? Okay, advantages of tree-based models. They are easy, they are simple models, and they are very interpretable because we can get this type of trees in order to understand how the model made the decision. Okay, the disadvantage is that they are prone to overfitting. Okay, so we have to deal with this. In order to deal with this, we come to another concept that is called ensemble learning, okay? Ensemble learning is the process of combining predictions of several models to improve the robustness over a single model. One of the most popular ensemble learning models is random forest, okay? Random forest, the idea here is to create a forest of decision trees, a lot of decision trees working together, okay? The final prediction of each one of these decision trees will be the majority voting or averaging of the results of each one of the trees. Okay. How we create these trees? Well, each tree is grown from a random sample of the data. Okay. This technique is called bootstrap aggregating or bagging. Okay. We choose only a random sample of the data for each one of the models. And also, each tree do not learn from all the features that we have, but only for a random subset of feature of for each tree. Okay. Okay, this is the idea. No, so this algorithm is very powerful. You will see publications using this algorithm because this is one of the most popular. But however, it has some limitations that are, for example, that each tree is built independently, so no learning from errors from the other trees. We don't have this learning from the errors from the other trees. In this sense, the third concept arises, that is gradient boosting. And in gradient boosting, the most popular algorithm that we find now in the literature is XGBoost, okay? And that comes from extreme gradient boosting, okay? So the difference is here is that XGBoost builds each one of the three sequentially, okay? So each one of the new trees corrects the residual error from the other tree, okay? And this may improve model performance step by step, okay? So its advantages are that are highly efficient, they can handle large data sets, and you will find that is the winning algorithm in many machine learning tasks, current machine learning tasks, okay? But however, it's a little bit more complex and less explainable than random forest, for example, okay? And in the case of multivariate time series forecasting, regarding time series forecasting, just say that this type of data, time series, is less exploited in machine learning compared to tabular data or imaging data, okay? And come with some specific challenge of the structure of the data, okay? It's data that is complex. It has a lot of temporal dependencies. We have to deal with specific things of the data, such as seasonality. And also we find a high correlation between variables sometimes, okay, no? So there are two ways of approaching this type of forecasting methods. One is more a classical statistical method and here in classical statistical methods, I include ARIMA, that is the most popular algorithm that is called for autoregressive integrated moving average. This algorithm is robust, efficient, automatic, very easy to implement, but however, is not effective when we have nonlinear relationships or complex problems, okay? So on the other hand, and here, yes, we are planning to use for assessing this type of problems, deep learning methods and more specifically, recurrent neural networks. Recurrent neural networks are capable of modeling short and long-term relationships in data, especially when we are using structures as LSTMs and GRU. But however, there are much more complex algorithms where we need to build them we need expert knowledge to build them, more complex architectures and high amounts of data that make this very difficult to train. Also, we need a lot of computational capability. I won't go in more detail with these methods because I would need a lot of more time, and I want to also explain a little bit one important concept when analyzing machine learning algorithms. In fact, two important concepts when analyzing machine learning algorithms that are explainability and interpretability. Okay, explainability and interpretability are two concepts that are difficult to differentiate. So I will try to give my idea of what I think about explainability and interpretability. In the case of explainability, what we are trying to explain here is understand and describe how a model makes its decision. It talks about transparency and being able to trace the logic of the model's output. But interpretability goes a step further, okay? Is the degree to which a human can comprehend the cause of a decision, okay? In other words, understand the inner workings of the models, okay? Now I will give you an example to understand how to assess explainability and interpretability in a practical case. For example, imagine that we have trained a random forest model that classifies the probability of having a second stroke, okay? What we have to do to assess interpretability? We should understand the reasoning behind the predictions, okay? So how can we assess this? Random forest is a very complex algorithm, no? So what we could do is to, for example, go and look for the most accurate decision tree from all the forest and try to understand the logic behind the decision tree, because it's easier to assess one single decision tree, even that this decision tree is not as accurate as the random forest. It can help us to understand the logic behind the model. Okay, this would be a way for assessing interpretability. And explainability, it can be better assessed because even that the model is complex, for example, we can determine the feature importance scores, okay? And this is something, for example, in random forest, we can extract the feature importance. No, the feature importance is something that we can extract after training our algorithm, and is a table of a score of this type. For example, in the first example of data that I gave you, this would be the feature importance. What is telling us, what these numbers are telling us? Well, where the number is higher, all the features would sum up to 1, and if the number is highest, it's telling us that is more important for the decision of the algorithms. In this case, for example, the age, but also the BMI and the average glucose level would be important to make the decision of having or not having a stroke. This is something that a random forest have. But then we have other explainability tools that help us to interpret, to explain models. Most of the common and classical machine learning models can be explained with these tools. These two tools are SHAP and LIME. Okay, SHAP comes for shaped additive explanations, and what these measurements do is measure the impacts of a specific feature on the model output for a given observation. Okay, in the case of LIME is similar, but it's not the same, because what LIME does is to create a local interpretable model, so that focus on what we do basically is to focus on creating a local surrogate model. Okay, so we create a simpler model that tries to explain each one of the observations of our system. Okay, the main advantages of SHAP is that can be focused on global and local explanations at the same time. When I say local explanations here, I mean for each one of the observations of our model, instead of having the global explanation, but with SHAP we can do both. But however, this is a method that requires a large computational capacity if we have big data sets, okay? In the case of LIME, it can be easier to interpret. The measurements and the metrics of LIME are often easily to interpret than SHAP, but It's centered only on local explanations, so is not able to capture the full complexity of the future explanations and interaction between each other. Unfortunately, I don't have a lot of time to show you the nice visualizations that you could do with CHAP and Lime, but I also leave you here an article about ischemic stroke that use all these measurements to explain some of the models that they are using, and it's nice to see all the possibilities of these two models. Okay, so more or less this was all I wanted to explain, and now I will give the word to my colleague Paula, that she will explain why not everything is about choosing the best performing model. So Paula.
Thank you, Carolina. I hope that you see it. So as Carolina mentioned, I'll focus on let's say the most ethical considerations about the implementation of AI, and in particular, I want to start with the reflection about the performance. So either if you are a machine learning developer, or if you are familiar with working with our profile, let's say, usually when we evaluate the performance of models, we just think about one of the metrics that Luis presented before. We usually talk about if the model has an accuracy of 0.84 or something like that, and we are very focused on trying to improve that even at the slightest level, right? So the thing here is that when focusing on this kind of evaluation, what we are leaving aside is the other implications on the human interaction. So as these kind of solutions is more prominent in our daily lives, it is important to also think about the impact on human freedom, let's say, and other dimensions that are considered with that, like autonomy, privacy, or also equity. Because at the end, machine learning tools are shaping our society, and that implies that we need to go in the direction that we want to go. So that leads us to the big question of what is the role that we want them to play in the digital world. And during the brief presentation that I'll share, I hope that we reflect on the different dimensions that I selected for machine learning. So the first one, and linking back to the presentation of Carolina, is about transparency. So it's very common that we all want transparency because it feels like something very good to have, right? But transparency at the end, it's just the means. So when we think about transparent models, it's not that you want access to it and you want to know like all the commas that are written in there, but what you really want is to understand what it's going behind. So transparency is just a means to the road of intelligibility. So what we want at the end is to understand what's going on, because information is power, and having power means that we are in control of the solution itself. So that is related to trust. And I wanted to think together about what the meaning of this term is, because when we talk about trust, maybe we don't think that trust is like in a middle state with what we know and what we don't know. If you know something, you don't need to trust it because you know it, right? So when you talk about trust is when you don't have all the knowledge that you would like to have. So usually, I think especially machine learning during the last year, we always talk about trustworthy and stuff. And then at the same time, we also talk about getting more access to everything. So this kind of trade-off with having trust and having full intelligibility into everything, it's a bit of a, let's say, not a straightforward relationship. And bringing that to something more tangible, it's quite difficult because all these terms are very abstract. So these ethical concepts at the end, they are very subjective, and there is not a unique solution or a unique definition. And I wanted to start trying to shed some light into the concepts that Carolina presented, for instance, in the case of interpretability. When we talk about interpretability, what we aim for is to get more understanding of the solution that is behind and understanding how it works and why does it propose to take the solutions that it proposes. But there are many kinds of interpretability to have. So maybe we can think about intrinsic or postdoc, meaning that we can think about the model itself, about the complexity of the model that we are working on, but we also can think of the interpretability of the solution on the relation of that solution. So once the model is trained and we get the prediction or prescription or whatever we are working with to understand how that was created. We can also think about model-specific or model-agnostic. For instance, there are some examples like the feature importance presented before that is model-specific. So there are some models that have this feature that can be exploited, but there are also some methods like Lyman shape that can be exploited independently on the model. So it's also different approaches that you can pursue. You can also have local or global explanation interpretation. So you can either go to understand the point itself. So what will happen for a woman that is 52 years and smokes, or you can just think about what will be the impact on the demographic of stroke patients. And you can also think, you can also have different types of interpretations. Like you can go for rationales, that is just the justification for a particular prediction. So to understand why this decision was taken, or also think about effective modifications. That's more related to the what if scenarios. Like in the example of that woman will be, what would have happened if that woman of 52 years didn't smoke? So then you have these counterfactuals that would allow you to understand better what's going on. So at the end, what I wanted to share with you is that even though that we are working in the direction of getting to know better why the models behave as they do, it needs to make a lot of decisions in the middle time to understand what really we want to detect from these models, right? So we want to understand it at local level, global level. So all these are small actions that allow us to make these concepts more tangible. And on a similar note, I wanted to talk about explanations. So on that, there is a very interesting video of Richard Feynman that talks about magnets and how the relation of these magnets work. So if you have time, I totally recommend it. And the idea here is that when we talk about making some models explainable, we really need to think what that explainable means in that sense. So for instance, here, this is the effect of pareidolia. That is when you see faces in animated objects. So here I can explain, oh, see, this pepper is happy, but this is just an explanation that I made up because I see it happy and that makes sense to me. So this is all. But trying to make up explanations that make sense and are sustained and that are based on a vocabulary that is shared between the emitter and the receptor is key to properly communicate on that and to properly make these models effectively explainable. So now let's say to widen the view of the ethical considerations of machine learning, I wanted to also talk a bit about fairness, and assuming that the more classical view of fairness it's already spread, I want to focus on the impact of modeling. So when we do a model of, well, what we aim to do with modeling is trying to capture the model as the world as it is. At the end, what we do is to capture what is quantified about the model, right? So we model the world as it is quantifiable. And then once we have a model that we then use in the real world, we will have an effect on the real world itself. So this impact of what we model, the model in practice, and then the results of this modeling that will shape again the data that will be captured in the future is important to keep it in mind because we are affecting the measurements of the future. So being aware of the impact of this machine learning put in practice is quite important to understand if this is the direction that we want to pursue. I wanted to share another example that is based on the Shirley cars, that is the ones that are shown here. When Kodak, let's say, launched the cameras like in the 60s or 70s, they had these Shirley cars that were the standards for calibration for the cameras. So to calibrate the colors, they used these pictures of white women to be sure that the colors had the right contrast and stuff. So what happened is that then when pictures were taken on people from different color shades, so let's say black people, the photos were terrible, that there was no contrast at all. And that at the end meant that there was a standard that didn't apply to everybody. And then the modelization of this standard even decrease or worsen the situation for let's say representative evaluation of the society. So this is especially important to have it in mind in the medical practice because the impacts can be, let's say, quite high. It is important to know what will be the effect of having a certain machine learning solutions in practice. And to finish, I wanted to talk about the role of autonomy. In medical practice, autonomy is one of the key values, as it is one of the pillars of bioethics. And having the respecting the autonomy not only of citizens, of patients is key to let's say to a complete and to a ethical treatment. So when we think about the role of machine learning solutions in the medical practice, we should be aware that most of the cases, these solutions are used as decision support systems. So they are used just to complement the decision that clinicians will take. So then autonomy should be integrated in the same way as it is now integrated in medical practice, right? So we should think about how well informed they are the end users of the solution, if these end users will be able to depict the different options that they have, so to create the decision space, and also if they will really be free to take those decisions. Because many times, or at least we have a lot of experience now published, that in many cases, the decision taken by people using machine learning as decision support tools is the algorithmic decision itself. So this is something that shouldn't happen in an environment where autonomy is really preserved and upheld. So this is something that, let's say, maybe it's not that integrated in the machine learning culture, but it's something that we really should, let's say, strive for and try to make this a reality, that it's at least it should be a default in the medical environment. So to close, I think maybe this could be a nice question to think about, like, can the digital future be our home? That this is really something that is up to all of us, and how we use these tools, how we design them, what do we want them to do, and how do we want them to apply to. So yeah, just let's think about all of us as proactive agents that we can shape the way that we can use these tools with. So yeah, thank you everybody on behalf of also my colleagues Carolina and Luis. It's a pleasure to be here, and we hope that you have learned something, or at least you found this interesting. So yeah, thank you everybody. And if you have any question, please go to the chat, or we can play around with the switching off and switching on mics. Thank you.
Okay. Well, I have one question. Well, maybe we'll read the questions, no? And if you want to talk with, you can raise your hand also. We have one question regarding Lyme. How do you think we can make Lyme for global explanations if we want to see the global behavior of the model explanation? Regarding Lyme, that is precisely designed to create local explanations. It don't have this. It's tailored for that. It don't have this framework such as SHAP to do global explanations from the local. What you could do is to sample your data, maybe to investigate the data that is most different, and to perform Lyme to this data that you feel that is being classified differently, or maybe cluster your data by different groups and perform Lyme in these different groups and see and check if there is consistency between the features. I assume that you could do that if you don't want to use, for example, SHAP, because you are planning to use Lyme and you prefer to use that. So that's what I would do in this sense. Okay.
Yeah, thank you for the answer. I'm curious about, can you hear me?
Yes.
Yeah, okay. I'm also curious, like, what I'm doing is like comparing the different techniques, for example, the Lyme, SHAP, and all the other explainable techniques, whether it is interpretable model or whether it is the black box model. So like, would it be the unfair comparison when we do compare the SHAP and, for example, the Lyme on a global, perspective, on the global behavior of the model, if we want to say? So like, Lyme is designed for the local, prediction, right? So it generates the explanation on the local level. So would it be fair to compare these both techniques? What is your take on this?
Well, if we want to compare, I would put them in the same scenario. If you want to compare SHAP with Lime, maybe you have to compare at the local level. And if you want to create a global Lime, but you have to tune up Lime, you maybe had to do this in the same way for SHAP, in the sense that if you want to compare these both techniques for local explanations, you have to select your samples in the same way. So this would be the first as to do from my point of view, no? But of course, this is something that should be explored. We didn't compare. Right now, we are extracting some explainability measurements from our experiments, but it's good also to compare how these two metrics perform, because this is something also to take into account, no? Depending on also the complexity.
Yeah, that is nice. So one more question I'm also like wondering, like what could be the possibility to evaluate the explanation? Are there any evaluation metrics for that? For example, if in the data-driven techniques, we do see the accuracy or F1 score when we are comparing the model. So what should be the evaluation metrics when we are comparing the explanations? So, yeah.
Good question. We have to research on that. I cannot give you an answer, but it's a good research question. I believe, no? How come we assess these explanations? It's something that we are starting to think, but I don't know if you have any suggestions in this sense. It would be nice also to hear it.
Yeah. Thank you for the nice webinar. Yeah.
Okay. More questions? Here we have federated learning is still vulnerable to privacy attacks like membership inference attacks, data reconstruction attacks, and attribute inference attacks. Which approach will be used in stroke analysis to tackle such privacy attacks? Maybe one colleague from Work Package 2 is here to answer that.
I can answer. I'm Stefano.
Hello, Stefano.
So, this is something we are discussing about, so it's quite difficult to say right now. But clearly, another question is whether the parameters the parameters that describe the random forest of the XGBoost can be actually shared without leaking privacy information. So this is not clear. Well, neural network model parameters can be in principle shared in a parameter server without leaking privacy information. We are not sure whether the same is possible for random forest and XGBoost, for example, because the tree structure reveal the structure of the data itself. So there are many research questions which are still open.
Yes, this is also for the following question, no? Because it goes in the same way, no? Okay. I don't know if any more questions.
There is another question above about ECGs that from Fateme, thanks for the great talk. Regarding the data, tabular data and time series are the only data being used for other type of data, such ECGs. Will be also considered to combine with tabular data. I can say that the ECG is also a time series data. So it can be treated like this. Also, in the bibliography, a lot of people is working in ECG and machine learning is extracting the different features from ECG and treat it like tabular data.
Yes, even if it is sensor data, you can use approaches of time series data, because at the end, sensor data can be treated as time series or signals. You can use also classical signal processing techniques to extract some meaningful features or do some type of feature transformation in order to obtain something that is meaningful depending on the problem. Then combining with tabular data, maybe what you can do is, for example, the time series. If you are doing a neural network, you are extracting some type of classification or reducing the complexity of this time signal into a tabular, some tabular features, and then you can combine with a classical tabular data, for example. It depends on the problem. Okay, so if there are not more questions, we are finishing now. So thank you very much for your attendance.
Thank you.
Yeah, thank you.